All right. Well, starting on motor theory and application, obviously, start with DC motors and how they operate. So DC motors are going to be run mostly by batteries and stuff like that. So this would be like any kind of hand tools. DC motors have come up a long way, even in the last couple of years. I mean, if you buy hand tools somewhat often, you might notice where a lot of them now are saying brushless DC motors. That's a big thing, getting rid of the brushes, getting rid of the carbon buildup that can happen with DC motors. So this is module 2. So this is, let's go backwards from the lighting. They have a DC. Let me look and see. All right, we're gonna watch a video to start this chapter. This is again one of those engineering mindset videos. Biggest thing, like pay attention to the different parts. That's what a lot of these chapters can be, just the different parts, not as much. For all intents and purposes for this class, I'd rather y'all know the parts rather than diving into the theory of how they work. All right. So page 1, motor theory, talking about DC motors. Pretty much, I mean, motors are pretty much electromagnets arranged in certain ways to create a spinning energy. It's essentially all that they are, and they've just come along further and further with how they're made. I mean, how they're made has been the same for a while, but they're becoming, especially DC motors, are becoming more and more efficient. But definitely super important in industry and stuff. I don't see you guys rebuilding motors, but it is important to know definitely the components and characteristics of how they work. On page 1, I don't have any of the trade terms highlighted, but if you look through there, those are a lot of the things that he talked about. You should know that armature is another name for the rotor, the part that actually moves on the inside of the motor. Commutator is what connects the electricity to the motor, essentially, with the commutator and the brushes. All motors are going to be rated by their horsepower. RPMs are important. You got to make sure you get the right type of motor. And then he talked about rotation. My first highlight on page 1, or my only highlight on page 1, is 110, how DC motors operate. Third paragraph is highlighted with the second bullet point. There are several characteristics of these magnetic lines of force that must be remembered when dealing with electric motors. They are the following, and then magnetic lines of force do not cross. If like he was talking about the magnetic lines of force and which way your electron flow was, and then I can't remember whose left-hand rule it is and stuff like that. Like I still struggle with that, like learning that every time. When I was in school, it didn't make sense, and I never used it in a factory or anything like that. So it's like him going through the 11 steps of how a DC motor operates, the left-hand rule of how electron flows. Don't get hung up on that. That's all I'm saying. Page 2, DC motor components. Second paragraph, first sentence is highlighted. 111. The armature is a movable electromagnet located between the poles of another fixed permanent magnet, as shown in figure 2. How is the, at least in the video, how is the armature made up of? What was it made up of?
Laminated sheets.
Laminated sheets. Why were they laminated?
To stop eddy currents.
Eddy currents. To stop, to not stop it a little bit, but to limit, reduce it to a smaller area. And just so eddy currents are a pure loss. That's one of the losses of an electric motor is eddy currents. Electric motors are super efficient, stuff like that, but that is one of the losses of an electric motor. Page 3, I've got the first sentence of that note highlighted. The brushless DC motor was developed to eliminate commutator problems in missiles and spacecraft operating above Earth's atmosphere. So usually that type of technology trickles down. So they started with NASA and stuff like that. Anybody know any other like inventions that trickled down from like spaceships and not spaceships, like NASA or anything?
GPS.
I mean, that's part of it. Satellites. So even simple like Velcro is NASA. Like that's a big one that just trickles down into stuff. But yeah, definitely brushless DC motors are a big thing because like it showed like brushes are connected to the commutator, which is connected to the slip ring, and that were made of like a carbide material, and those as they hit those grooves that wears them out over time, and they can be replaced. You usually find by the time somebody decides to replace them, there's nothing left and there's damage to the commutator, but they do have the ability to be replaced. But brushless DC motors are probably what everything's heading to, at least on the smaller side of motors and stuff, within the next decade. Flipping over to page 4, you can see the different types of brushes on page 4. So they just have if you're looking up on the board, you can see how they all have a radius on them in order to touch the commutator segments. And then a spring with a wire on it. So this is what the actual electricity is flowing into and out of for the motor. So you can have your commutator segments on theirs. They had just 3 different segments, but you can have multiple different segments to like the video said. The more you have, the more windings you have, the smoother the operation is, especially if you're running at lower RPMs. But they usually have some form of spring. I've seen this mechanism mess up before, and this is a hard one to fix. Like, it's kind of like some of this is kind of little flimsy metal. The spring is different on most of them that I see, but all it is to change the brush is take this little clip off, move the spring, the brush pulls right out, and you can change it. But there's different types of brush holders. This is the clamp type is usually the type that, at least that I've seen in motors and stuff like that, but it's usually all smaller type motors. 112, the neutral plane. Second paragraph, first sentence is highlighted. In the neutral plane, no torque is produced and the rotation of the armature should stop. So you remember, like, if it only had one winding, and if the winding was straight up and down in between the north and south magnet, all the lines of force or all the magnetic lines are passing straight through it, and there is no force pushing that winding one way or another. That's what the neutral plane is. So technically, if somehow the motor stopped right there at the exact right spot, it wouldn't start back up until something gave it a little bump. And that's why they don't have a one winding motor. That's why there's multiple windings. That way it can't get stuck right there. But that's one of the disadvantages. Once the motor started, that inertia, the motor spinning just brings it past the neutral plane as it's moving. That's all I've got for pages 4 to 5. Flipping over to page 6. I don't have anything in armature reaction. It's just talking about like how the armature responds to the magnetic lines of force and the spinning motion. That's essentially what they want a motor for, turning a magnetic lines into a rotating torque. Counter electromotive force, CEMF. Second sentence is highlighted in 114. The magnetic field is produced by the field poles, and a loop of wire in the armature turns and cuts this magnetic field. So they'll even have, like on the video, they just had a north pole and a south pole magnet. Other motors have multiple magnets, not just on the horizontal, but on the vertical plane as well, to keep that thing spinning. But yeah, it's just talking about the field poles, magnetic lines of force being set up for the motor. Page 8 and 9, they go through kind of what he did. I don't have any highlights on either one of these pages, but it goes through and talks about the lines of flux, and which way they're pushing. And then once you start running current, through the armature, like how it forces the motor to start spinning and stuff changes. He did a good job of going through that, but you can see like right here, they're starting in the neutral plane, but as soon as that armature turns, you can see these magnetic lines of force are changed, but it's crazy. Like even watching it go semi-fast on the board, that is a minuscule fraction of how fast this stuff happens. So it's not like they're even pulled out this far, because by the time it's constantly changing is kind of what I want you guys to know. They just show like the different forces being made at different positions of the armature. They have like the starting resistance. Like starting resistance for DC motors is a lot higher because they usually have a larger neutral plane. They go through that. I don't have any of those equations highlighted. Moving on to page 10. And then one equation that is important is horsepower. Figuring out horsepower, I've got horsepower equals watts over 746. So if you're wanting to convert your electricity into a horsepower number, you can take your watts divided by 746, and that gives you horsepower. 1 horsepower is 746 watts. DC motor types, a bunch of different types, and it's just the different types vary on how the windings, how the motor windings are wound inside the motor, how the armature is set up. There's different advantages and disadvantages based on how this is done. Page 10, 120 DC motor types, third sentence is highlighted. The shunt motor has the field coil connected in parallel with the armature or rotor winding. Pretty much means there's a big coil on the outside that's connected to the brushes and the commutator. This is, anytime you hear shunt in the electrical field, that just means like a separate path for current to flow to create something. Because we know like we add resistors and stuff to circuits to control the voltage and whatnot in a series circuit. So they're doing the same thing. They're getting the main two things for a motor is speed and torque. So you can play with your speed and torque values by using a shunt DC motor. I would for all of these, like it's not a bad thing to read through like the operating characteristics of a shunt wound motor, because they're fairly common. But you have torque, speed control, and speed regulation. None of those are highlighted, but it wouldn't be a bad thing to read through. I have the last sentence on page 11 highlighted. This motor is suited to applications that require a relatively constant speed over a wide load range. This motor is suited to applications that require relatively constant speed over a wide load range. Series DC motors, page 12. So series is kind of like a shunt motor, but the winding is connected differently. So you can see this one stuff is connected in parallel. This is connected in series. That's why it's called a series DC motor. Top right of page 12, that sentence up there is highlighted. The series motor is used where there is a wide variation in both torque and speed requirements, such as traction equipment, blowers, hoists, cranes, and so forth. Compound DC motors. So these are motors that can have different coils hooked into the motor to create different things, and they can change them as the motor's going. 1, 2, 3, first two sentences are highlighted. Compound DC motors are used whenever it's necessary to obtain speed regulation characteristics, but not obtainable with either the shunt or series wound motor. Because many applications require high starting torque and constant speed under load, the compound motor is used. And go through the different characteristics of torque, speed control, speed regulation. That's all my highlights for section 1. You got a couple questions on page 14 and I got right quick. Right. Number 1, when studying the operation of electric motors, it's important to remember that magnetic lines of force
Do not cross.
do not cross. B2, a motor with field coils connected in parallel with the rotor winding is a
Shunt motor.
shunt motor. AC motor operation. It's gonna make more sense. We're gonna watch another video. I know these are a little long, but it helps. It definitely helps me in explaining some of this once when we're going through it. But we're gonna start AC motors.
Is what?
Bearings are usually they cause a motor failure a lot more times than not. Improper greasing motors is very important, and it is very important to use the right grease. Usually it's some type of, like, it's usually a blue, I forgot the chemical term for it, but you do not want to mix different types of grease in motor bearings. Another thing is, like, they show pictures of like the winding inside of an actual motor, and it just looks like a lot of bare wires running through there, right? They're not bare. They have these motor winding wires are, I think it's like a glass insulation that's on them, so they do not touch each other on the inside. That's another failure if that insulation on those winding wires wears off. But they are isolated from each other by insulation, even though all of them look like bare wire. Like all this looks like bare wire, but these are all insulated from each other. Like there's not current passing in between wires. At least there shouldn't be. That's a failure if you have like a face-to-face short. And then, so in a DC motor, the electricity is passing into the moving object itself, and then you just have stationary magnets on the outside. So the armature is actually, the electricity is actually pushed through the armature, and that's what makes it spin. An AC motor is different. The electricity passes through the stator, or the stator casing housing, all kind of interchangeable words. The electricity is passed through that, which makes the rotor spin. It's important that in the AC motor, this is called the rotor, not an armature. So this is just a rotor. In the DC motor, it can be called either one, but in an AC motor, it's called the rotor. Not important, but did y'all know in World War II they found spies by making everybody say the word squirrel?
Squirrel.
I just noticed it because the way he said it, like a lot of people in Europe and Germany and stuff like that can't say squirrel like we do, but they say like squirrel. Squirrel cage induction motor is the most common type of electric motor. So that's going to be important. Like it's always like if you see this arrow right here, this would be your rotor. And it's always like the rotor is trying to catch up with like the north, like the end of this is going to be a south pole, and it's going to be trying to catch up with the north pole. But the north is shifting constantly, and it's never gonna, like it's always, the north pole is kind of pulling the south pole along the motor. It's kind of how it works. And then just so you know, like the speed of the changing north pole around the motor, sounds weird, is the synchronous speed. You can get synchronous speed motors to where it's like it's locked into where it's a constant speed, but we'll talk about that. But just know that the speed of the north pole and south poles changing around the stator is known as the synchronous speed. The other way is the more common way of connecting a motor. Just a quick thing, like I said, most of the time this is called a star or a Y. Whenever it's spelled Y, it's W-Y-E. So this is the more common one. Delta configurations are still used. That a lot of maritime industries or the Navy uses this. And the reason for that, without getting into too much theory, is you can drop one of these foils and it'll still run. Because you still have you still have a connection between all three lines, but you'll run at a lot higher current. But something happens on a ship out in the middle of the ocean, stuff like that, you drop a leg for whatever reason, you can still run and get back to fixing stuff or something like that. Back to the book. So synchronous speed is important. I don't have it highlighted, but it is. I would be very surprised if it's not in the book of questions. The speed of the revolving field of the stator, which is dependent on the supply, frequency, and number of poles in the stator winding. How AC motors operate, 210, first sentence. AC motors consist of two parts. The stator, which is the stationary part, and the rotor, which is the revolving part. Rotating fields, 211, second paragraph, first sentence is highlighted. Polyphase AC is brought to the stator and connected to windings that are physically displaced 120 degrees apart. Usually, like polyphase AC, like that's three-phase. You're not ever going to have two-phase. I think two-phase is a thing in other countries somewhere, but it's not widely used. But three-phase is what they're talking about. Rotor behavior in a rotating field, flipping the page to 16. You can see like they're going through the different 7 different points of the rotating magnetic field for three-phase, and you can see how where the forces are at different points. It's just like the video talked about. 4 different questions are coming from the bottom left sentence in 16. The synchronous speed of the motor is given by the equation. NS, which is the synchronous speed. Don't get that mixed up with number of secondary. Okay, we went over transformers. Don't get that confused with that. NS is the synchronous speed in RPMs is equal to 120 times the frequency over the number of poles in the motor. So that is
questions.
4 questions come off of that one thing, which I think they just have you figure out what the synchronous speed of the motor is. So just looking at that equation, how do you change the speed of a motor? What are your 2 variables?
Your frequency, number of poles.
Frequency and number of poles. Number of poles is difficult to change because that's a hard set component of the motor. They do have multi-pole motors, but it's kind of a thing in the past. How do we change the speed of the motors? Like what piece of equipment do we use now? So the other thing is changing frequency. Right. So we have what's called VFDs, or variable frequency drives. So that's how it changes the frequency of the motor, which changes the speed of the motor. So very, very simplistic, while AC, like, I know this stuff is confusing now. But if you think about it, like, all of the electricity is passed through a non-moving part, the stator, right? And then it comes out of the stator. The rotor itself, while a current is induced into it, it's not touching anything. It's floating on bearings and then connected to something else. Like, there's not anything actually electrically connected to the moving parts. So it's a very, while it is a little complex stuff for especially brand new, new to electrical and stuff like that, it is a pretty simple machine. The simpler you make a machine, the more rugged and stuff like that they are. Page 17 talks about different characteristics of motors, induction, torque, slip. So the slip is the difference. Remember I talked about synchronous speed and like how the north magnet follows around and then the armature is trying to catch up with it. The slip is the difference between the two. I don't know that I have a highlight on that, but it's good to know what the definition of slip is. Not like all the math on there that's figuring out what slip is, like who cares? I don't know who does that math, but that is not important until, I don't know at what point that's important. I don't have anything else highlighted on page 17. Or 18 and 19. Starting current, this is important. The starting current, when you start a motor, is the highest that it will be, and it is a lot higher than the synchronous speed. So you have your graph on page 18. So the first, like, it's called block rotor torque whenever you start up a motor, and that's just because the rotor is stationary. So until that thing gets spin, the more that thing, or faster that's spinning, the more inertia it has, the easier it is to spin almost. But whenever it is dead stop, and even starting with some type of load, whether that be a fan or pump or whatever on the end, that is where you are going to get your highest amount of torque required, which means the highest amount of electricity required, which means the highest amperage. So a lot of times that's why motors trip out on initial startup and stuff like that. And sometimes it means that a gearbox has failed and there's too much torque, or something else has failed, or a bearing has failed and it's causing that initial torque to spike. But you can see, like, starting torque right here, I guess that's torque. Like, you have to have the most torque right here, and then once that motor speeds up all the way to its synchronous speed, the torque, it doesn't require as much torque. I guess it does talk about starting torque. It is, like, we're gonna go through this probably in this chapter. I'm getting ahead of myself, but it is good to know, like, at the bottom right of page 18, that last sentence, because of this high inrush current starting protection as high as 300%, a full load current must be provided. And that's what we will go. I don't know if it's this book or the electrical 3 book for next time you guys are here, talks about that, but you have to size your fuses and breakers for 300% or whatever the normal operating amperage is. But no hard highlights on 18 or 19. Page 20. They talk about power factor. Remember, if you have an AC induction motor, that's gonna cause your power factor to be worse. You're gonna have more K-bar, so more of that foam on top of the beers. What induction motors are gonna cause. 220 3-phase induction motors. We're going to talk about figure 27. Oh, reversing rotation 210. That from page 19. What's that? 2 sentences. All you have to do for a 3-phase motor on page 21. The only thing you have to do to reverse the direction of a 3-phase motor is change any 2 of the windings. And you can see that normally, like in the book, it's showing you're changing over L2 and L3. Standard, or at least standard for everything I've done, is you swap L1 and L3. You leave L2 alone. And you can do that by just swapping the wires, or if you have a three-phase motor, you guys are gonna work with contactors, and you can have reversing contactors that will change that over for you without making actual disconnections. 221, squirrel cage induction motors. First sentence is highlighted. The squirrel cage is the rotor most commonly used for three-phase motors. Page 22, first sentence on page 22 is highlighted. The speed of a three-phase squirrel cage induction motor depends on the frequency of the applied voltage and the number of poles. Next paragraph, the whole thing's highlighted. The squirrel cage rotor motor is a general purpose motor. It's used to drive loads that require variable torque at relatively constant speed with high full load efficiency. Uses include powering blowers, centrifugal pumps, and fans. Because of the absence of any moving electrical contacts, they are suitable for use where they're exposed to flammable dust or gas. That's a squirrel cage, by far the most common type. It's not even close. 222. Wound rotor induction motor. So a wound rotor actually has electricity that is injected into the rotor. And this is to change characteristics of the induced voltage on the rotor. My highlight on page 23 is in the top right of the page. That one sentence, you'll have a couple questions coming out of that one sentence. In a wound rotor induction motor, the insertion of a resistance in the rotor circuit not only limits its starting surge of current, but also produces a high starting torque and provides a means of adjusting the speed. I'm wrong on this. You're not injecting current, you're injecting resistance to create higher starting torque. You can kind of see how that's wired up right here. So you have the stator, which is constant. You have your rotor, which is wired up. This is slip rings, which is kind of like, just being honest, I don't think I've ever changed out one of these motors. And if I had, all of this was internal, and I just had to wire up the motor like normal. But these are slip rings that are kind of like the part of the DC motor commutator. And then connected to different resistances to change your starting torque. Next page, synchronous motors. Whole thing's highlighted 230. The synchronous motor is a three-phase motor that operates at synchronous speed, which is 0% slip. From the no load conditions to full load conditions, these motors are used in precision applications. Nothing in operating characteristics construction. On the right-hand side of the page, second to last paragraph, first two sentences are highlighted. To allow this type of motor to start, a squirrel cage winding is added to the rotor to cause it to start like an induction motor. This winding is called an armature winding. I think that's right. Something like that.
Must be French.
Sounds like it.
Just swap.
Yeah. It's like Mansour, but
Yeah, nothing else highlighted. It's got the principles of operation stuff. And while there are a bunch of different types of these motors and stuff, again, the most common that you are going to mess with is the squirrel cage, most basic type of motor, and that's because they're the cheapest and most rugged, least moving parts, stuff like that. Page 26 and 27. I've got no highlights on this, on these 2 pages. They talk about synchronous motor pullout, torque angle, stuff like that. I'm not interested in talking about torque angle and whatnot. I don't feel like that's important to what you guys are doing. 240, a little bit different. Single phase induction motors, so also super common. Obviously, anything at your house that runs on motors, so your dryer, your blower, your fan blower for your AC, your disposal, all those use a single phase electric motor. Which is the highlight. 240, second paragraph is highlighted. Example of many applications of single phase AC motors today are refrigerators, freezers, washer dryers, power tools, copy machines, heating systems, water pumps, computer peripherals, and various small appliances. Can't change directions of a single phase motor. They design in certain ways to spin in certain ways. You do switching the wires on a single phase motor does not swap the direction. They do have a different way of starting. So so in order to get that synchronous speed started, so to get that north pole right ahead of the south pole of the rotor, in order to do that, a capacitor is used. You use that capacitor like I think we've talked about capacitors are kind of like batteries. They can store an electrical charge. And then when you need it, it can kind of jolt. So it jolts that stator to switch positions, and then the rotor starts to try to keep up with it. Anybody ever have a fan or something that you've turned on and it sits there and does something like this, like sits there and shakes, and then you take a pencil and spin it and it'll start up? Y'all ever had something like that? It's fairly common, but usually what's happened with that is your capacitor's gone bad. Or if you have a house where your air conditioner outside isn't working and they come and replace your capacitor, it's because the fan won't spin or something like that. But you can take like a stick or something and spin it, and you're acting as the capacitor and getting that synchronous speed started and getting it going. Once it's going, it's fine, but it has to have that jolt to change the magnetic poles in order to get it start spinning. Split phase induction motor, nothing highlighted in that. Capacitor type induction motor, that's what I've been talking about. Flipping over to page 30. The first full paragraph, first sentence is highlighted. The net effect of the capacitor is to give the motor a starting torque of about 4 times its rated torque. Nothing else highlighted on 30 and 31. Flipping over to 32, they talk about capacitor start and run. Just the slip, and then the there's not. Yeah, I don't feel like there's any. I'm not going to talk about that too much. Next type of motor is the shaded pole induction motor. Online test questions, second to last sentence before 245. However, it has low starting torque, low efficiency, and high noise level. Second to last sentence before 245. However, it has low starting torque, low efficiency, and high noise level. Single phase synchronous motor. Nothing on that. That's just a little 1 sentence section. Flipping over to page 35. Multiple speed induction motors. A few highlights in this one. First sentence in 246 is highlighted. The speed of an induction motor depends on the power supply frequency and the number of pairs of poles used in the motor. Remember your equation, NS equals 120 F over P. Only way to change the speed is change the number of poles or the frequency. Multiple winding motor, the bullet point, first bullet point, the whole thing is highlighted. Multiple winding, in a multiple winding motor, 2 or more separate windings are placed in the stator core slots, one over the other, as shown in figure 46. For example, a 4-pole winding can be positioned in the core slots and have 2-pole winding placed on the other and arranged so that only one winding at a time can be energized. Key in on this last sentence. Switching speeds is normally accomplished by switching contacts that are in the motor controller external to the motor itself. So that's like this one. You can connect 2 different windings. So one winding would be to start it. So that would be your 4-pole. So that would be like your lower speed, get more torque out of it. But once you, like your equation, 120 F over P, so you reduce your denominator. So that's going to increase your speed, right? So then you can go to a 2-pole. Why would you not want to start with a 2-pole motor?
Because it'll get stationary.
It can be stationary, but it's going to be an insane amount of torque, which is an insane amount of current initial inrush. Remember when these motors start up, they can have up to 300% of their initial torque that's needed. So the lower amount of poles you have, the higher that torque and the higher the current has to be. So they'll go from 4 to 2, because once that motor's spinning, it's a lot easier to make spin with a 2-pole motor rather than 4, it's easier to make it faster. Next bullet point, first sentence is highlighted. Consequent pole motor. Consequent pole motors have a single winding with 2 speeds. And then page 36 just shows the different 2 winding, 2-speed motor, high speed consequent pole motor, low speed consequent pole motor, and the single phase consequent pole motor. I think I've ever seen it. Synchronous motor. Looks old. You got 4 questions on page 38. I think we're through most of the harder theory stuff right now. So each of those 4 questions, take a few minute break. We're not gonna make it through this. Actually, we'll answer those 4 questions. We're gonna do one more section and then we'll take lunch.
Just one that has.
Saying this is not here, but you can use that one in case you need it for, I think the last section was. Is everybody done with the section review? No, I've realized some of the work. And, section 2 review, number 1, the motor has 4 poles and is operating at a frequency of 60 hertz. The synchronous speed is 1800. So synchronous speed is equal to 120 F over P. They gave us 120 4-pole.
Yeah, full 60 hertz.
60 hertz, which is, 60 hertz is what?
The frequency.
Frequency, but that's what we run in the United States, right? We run at 60 hertz, so that's, you plug into the wall, you're gonna get 60 hertz. At 1800. 2, the type of motor most likely to be used in a location with flammable dust and torque fluctuation. Squirrel cage induction motor. 3, a type of motor used in precision applications that require constant speed with 0 slip. Synchronous motor. 4, a heating system is most likely to use single phase induction motor. Section 3, variable speed drives. So we'll go over this a little bit. I've got there's a pretty good lab I have that you guys will do next time you're here. Samuel, I'll probably have you do it. That's electrical 3. Are you stopping electrical 2?
Yes, sir.
3. But we have a pretty good VFD lab out there that runs through stuff, because a lot of people get, it's a variable frequency drive is very complex in how it operates, but controlling it is not that bad. It's just a bunch of different, it's got probably 40 different settings that you just have to turn on or turn off, and that's just for like ramp up speed, ramp down speed, stuff like that. They're not super difficult, but they do have just a bunch of different components. And if you get into learning how VFDs work, there's kind of different sections of a variable frequency drive that do different things. If that makes sense. 310, adjustable speed loads. Right side of the page, second paragraph, first sentence is highlighted. For a constant torque load, the torque remains constant throughout the speed range, and the horsepower increases and decreases in direct proportion to the speed. Skip a paragraph, and the second to last paragraph on page 39, the whole thing's highlighted. A constant horsepower load requires high torque at low speeds, low torque at high speeds, and thus constant horsepower at any speed. It applies to applications such as lathes, lathes requiring slow speeds for deep cuts and high speeds for finishing. Usually very high starting torques are required. Page 40. They go through like torque speed curves, which we talked about a little bit. I don't have any highlights in that. Motor heating. So a lot of larger motors have heaters on them. That's due, like you don't want to start stuff up cold, so you have heaters, like usually 120 volt heaters on big motors. I mean, like the motor heaters that I've seen, the motors as big as half this room. My highlight in that is the second and third sentence of 3.1.2. A factor to observe is motor heating. When operating a motor that at reduced speeds, the ability to dissipate heat is also reduced due to the slower cooling fan speed. That is not what I thought that was talking about. That is what I just said does not relate to what they're talking about. They're just talking about cooling off the motor. So the motor has all those fins on the outside, which I don't have a picture of, but those are cooling fins. I assume we're going to talk about motor heating at some point, but this is just talking about the fan. You have to make sure the fan's blowing the right way. If the motor's super dirty, it's not going to cool as well. But yeah, you want a motor warm to start up, but you don't want a motor to get too hot because it's going to fry the grease that's inside the bearings and stuff like that. Motor speed control. This is going to talk about AC and DC and like switching back and forth between the two. Flipping over to page 42, varying the speed of a DC shunt motor. Second sentence is highlighted. Basically, there are two ways of varying running speed of DC shunt motor. I have the second bullet point highlighted. Adjusting the voltage and current applied to the armature. As the armature voltage is increased, the motor speeds up. This method is shown in figure 54C. 3.2.2, varying the speed of an AC motor, page 43. It goes through that equation again for your synchronous speed. Last full paragraph in the bottom left, the whole thing is highlighted. When variable frequency speed control is employed, the motor supply voltage cannot be allowed to remain at a steady value. The magnitude of the motor voltage must be increased or decreased in proportion to the frequency. That is, the voltage to frequency ratio must remain approximately constant. The voltage to frequency ratio is sometimes referred to as the volts per hertz ratio. Going on to page 44, braking methods. You guys will be doing we'll see. We'll be doing braking methods on that trainer for sure. I don't know if it's this time you're here next time, but I'll get y'all on the motor trainer. It's probably going to be next time. But there's a bunch of different ways of braking without just using, like a lot of times they just use a brake on the back end, like a friction brake. But there's ways of injecting electricity the opposite way into a motor in order to stop it. If you have, because sometimes you have like a skill saw or something like that, you let go of the trigger, the blade keeps spinning. Nicer skill saws, when you let go of the trigger, it goes there's a braking method that stops the motor. So sometimes it's important to have different types of braking methods. 3.3.1 DC injection braking. First sentence is highlighted. DC injection braking is a method of braking in which direct current is applied to the stationary winding of an AC motor after the AC voltage is removed. Dynamic braking. First two sentences of dynamic braking is highlighted. Dynamic braking is another method for stopping a motor. It's achieved by reconnecting a running motor to act as a generator immediately after it's turned off, rapidly stopping the motor. Next paragraph, that short paragraph, the whole thing's highlighted. Dynamic braking of a DC motor may be needed because DC motors are often used for lifting and moving heavy loads that may be difficult to stop. For example, forklifts often use dynamic braking. Everything on page 45 is highlighted. The top of page 45. The generated CEMF, you need to know that stands for counter electromotive force. CEMF is counter electromotive force. Decreases as the speed of the motor decreases. As the motor speed approaches zero, the generator voltage also approaches zero. This means that the braking action lessens as the speed of the motor decreases. As a result, the motor cannot be braked to complete stop using dynamic braking. Dynamic braking also cannot hold a load once it's stopped because without the generated CEMF, there is no more braking action. For this reason, electromechanical friction brakes are sometimes used along with dynamic braking in applications that require a load to be held or in applications where a large, heavy load is to be stopped. All right, a little bit shorter lunch since I'm not giving you all as much to do. You just got 3 questions on the section review. 11:24, let's say 12:15. Go over that, 45 minutes. 12:15, be back from lunch.